So we have to define some things. So thermochemistry is studying the relationships between chemistry and energy. That's what this chapter is about. Well, what is energy? Scientifically, energy is the capacity to do work. It's not doing the work, but it's that you have the ability or the capacity to do work. Okay, what's work? Well, work is a force acting over a distance. That definition is a bit different than what we use in real life, isn't it? Oh, I have to go to work. Well, you can't go to work in this sense. But if I push this calculator across this surface, that is doing work. I applied a force to an object and I moved it over a distance. That's work. So energy is the capability of doing that. And then we have heat. Heat and energy are kind of hard to pull apart sometimes. Heat is the flow of energy that's caused by a difference in temperature. So energy can be exchanged between objects by contact. So if you think about, you go to Starbucks or Dutch Bros and you get a cup of hot coffee and you hold it in your hand, right? You feel heat, right? You feel it feels hot because the coffee is hotter than your hand. And so heat is this flow of energy from the coffee to your hand. Unfortunately, that does not in itself give you any energy to do your work, right? You have to drink it and get the caffeine. But that's what heat is. It's the flow of energy based on a temperature difference. So we can think of energy as a quantity that an object can possess. And I'll get into this later, but in many ways, energy is like money. It's something you can have, okay? So if we look at this example, here we have a billiard table, pool table, and we have this ball moving. That rolling ball has energy due to its motion. Heat and work are ways that an object can exchange energy with another object. Heat happens because of temperature difference. Work happens applying a force through a distance. So when this cue ball, the white one, runs into the purple ball, we get a transfer of energy. Mostly it'll happen as work. And now the white ball has very little energy and the purple ball has all the energy. And so the white ball's sitting here and the purple ball goes speeding off. Right? The kinetic energy was transferred from the white ball to the purple ball by a collision. So we see that energy can move out of an object. Here, the white ball lost the energy, and it can flow into an object. Its energy went into the purple ball. Well, let's get a little more into these types of energy. Kinetic energy is energy of motion. An object that's moving, that rolling ball, has kinetic energy. Thermal energy is a subtype, a different form of kinetic energy. Here, the movement is not of the object through space. The movement is of the particles in the object. So I talked about the solid, liquid, and gas state of students, right? And you guys are in the solid state right now. And you're at a pretty low temperature. Everybody's sitting pretty still, right? What if we got a lot of energy, the temperature went up, right, so to speak, and then we're just like squirming, right? I just can't sit still, I'm so uncomfortable, blah, blah, blah. There's more movement, right? It's not movement across the room. It's movement of the particles where they are. But that's temperature. Temperature is kinetic energy of the particles. It's not moving through space. Potential energy is energy of position. So it can be position, a ball raised above the table has potential energy because when you let it go, gravity's going to pull it down, and it's going to move, right? So yesterday I dropped the meter stick. Let's just do that again. So if I hold the meter stick out here, it has potential energy, because when I let go, it falls to the floor. It was moving, right? The potential energy got transferred into kinetic energy. The other type of potential energy, not, elevated above a surface, is chemical energy. And here, again, it's really related to position, but it's the position of the electrons and the nuclei in the atoms and molecules that form that substance. Some compounds are kind of like compressed springs. They have a lot of stored potential energy. And when you release that, it comes out. So the iron in the chemical hand warmer has potential energy, because when you bring oxygen in, this reaction occurs and heat is released. So this is a flow chart. Energy is the capacity to do work. There's kinetic energy due to motion. The one that's most important for chemistry is the thermal energy, and that's the energy associated with temperature, which is the kinetic energy of the individual particles, how much they're moving. In a solid, they're just like vibrating and wiggling. In a gas, they're actually zinging around faster. The other kind is potential energy due to position or composition. Chemical energy is what we're most interested in, and this has to do with the positions of electrons and the nuclei. So the introductory quote mentioned the law of conservation of energy. Here it is. It's a lot like the law of conservation of mass, just switch mass for energy. The law of conservation of energy states that energy can neither be created nor destroyed. So we can transfer energy from one object to another object. It can go from one form to another form, but energy cannot be destroyed. It also cannot be created. So this example, dropping this ball, gravitational potential energy, you drop it, and just like the meter stick, it's falling. Now it has kinetic energy. It's going to hit the table, it might bounce a little bit, and it's going to stop, just like the meter stick did. It's still laying there on the floor. What happened to that energy? We had potential energy turned into kinetic energy, and now what is it? It's heat. So it's not enough that we can detect with, by touch, but the energy went into heat, which, is the vibration of the particles in the meter stick and the floor, or the pool table and the ball. And on a large enough scale, it is hot. So here, pushing on a spring, you're pushing against the forces that maintain the spring shape, and so it's storing potential energy. When you release that, the potential energy is transferred to the ball sitting on top of the spring and shows up as kinetic energy. So we can transfer, we can change the kind. So we're talking about, transferring energy. We have to identify what we're transferring it between. So we talk about the system and the surroundings, and those would be defined in the particular situation that you're talking about. So the system is going to be whatever you're interested in studying, or whatever the problem is telling you you should be interested in. It could be your hand. It could be the whole room, the temperature of the room, right? In the hand warmer, the system would be the iron that's reacting in the hand warmer. The surroundings, that's everything else in the universe. The whole universe. Now, most of the time, we don't have to consider the whole universe. We can just consider stuff near, right? So the hand warmer is probably not going to affect anything in Nebraska, right? if you open one here in California, it's too far away. But it's going to affect your hand. If you're talking about the chemical hand warmer as the system, then your hand, the glove, the air around it, those are all part of the surroundings. The energy is going from the hand warmer into the surroundings. Any questions? So conservation, because energy is conserved, we know that whatever energy is lost by one thing must be gained by something else. It could be in a different form. It could be spread out between several different things, but it's not destroyed. And also, if something gets energy, it had to come from somewhere. So it's kind of like money. You know, if I buy something from you for $10, I lose the $10, you get the $10, but there's still $10. It didn't suddenly become $9. Now, if you figure tax in, right, maybe the government gets some of it, but the money still exists as $10. It's just that the government got some, right? So here, looking at energy like a gas gauge. So these tanks are the same size. They're both, this one's half full. This is our system energy gauge, what we're interested in. And this is the surrounding energy gauge. This is a quarter tank, and this is half a tank. After the energy transfer, the system has lost a quarter tank, and the surroundings have gained a quarter tank. What's lost by one is gained by the other. Total amount of energy is constant. So energy can be measured, so of course we have to have units. Here's our kinetic energy equation, 1/2 mv squared. So if we use SI units for mass, the SI unit for mass, the base unit is kilogram, length is a meter, and time is a second, we end up with kilogram meter squared per second squared. And that is given the name joule. So joule is a unit of energy. It's pretty small. 10-watt light bulb uses 36,000 joules in an hour. 10 watts. So we'll often see kilojoules. A kilojoule is 1,000 joules. So the abbreviation is capital J. Another unit of energy is calorie. So lowercase cal. It was originally the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. It's still really, really close to that, but it's defined to be exactly 4.184 joules. The calorie we talk about in everyday life, you know, that's on the package of cookies or whatever, that's a nutritional calorie. That has a capital C. And its abbreviation has a capital C. So if you have a worksheet problem or an exam question and you've got lowercase c's and uppercase c's, they are different. It's not a typo. And I might try to trick you with that one. I think I've done it before. So you've been warned. So this nutritional calorie is 1,000 regular calories. So really it's just a kilocalorie. And then there's a lot of other units. One you might have heard of is the kilowatt hour. And that's what PG&E uses to measure how much electricity you're using. Energy conversion factors. This regular calorie, 4.184 joules. The nutritional calorie, or kilocalorie, is 1,000 of those, and 1,000 times the amount of joules. And a kilowatt hour is, this many joules. I'll give you any energy conversion factors you need on an exam. This table is just kind of interesting. You can see comparison of, how much energy these different things require in the different units.